Wednesday night at about 8:30, and I just found out that class is going to be canceled again tomorrow. And I've decided that we can't afford to get two whole close classes behind. And since tomorrow is a double block, I've decided that I'm going to try and take you through the two notes that I was planning on doing with you tomorrow, and sort of walk you through them in this video, in two videos actually. Tomorrow we were going to start a new concept, a new topic called limits, and this is something that you've never seen before, I don't think. And it's sort of difficult, and I think it'll be hard for you to understand it with just the notes. And so my plan is to try and sort of walk you through these notes as best I can. I'm sure it's not going to be as good as if we were actually in class, partly because I won't be able to ask you questions to find out if you're understanding, and partly because you won't be able to ask me questions if you're not understanding. But I hope that this will be better than nothing, and if you can go through these notes and try the homework at the end, I think we can be pretty well caught up for when I see you again on Friday. So, today we're looking at, in the first note, the concept of a limit. You can see here in the objectives we hope to understand the concept of a limit, to be able to solve limits numerically, to be able to solve limits graphically, and to understand the difference between one and two-sided limits. That's our objectives for the end of the note. I don't think that probably means very much to you right now, but hopefully at the end of the note, if you go back and look at those four objectives, you'll be able to feel like we've accomplished them. So, to talk about a limit, I want you to start by picturing in your head, if you will, the graph of y equals x squared. Now, of course, that's a very familiar graph. You know it very well, that parabola concave up coming from the origin. And imagine if you are on a point at the origin and you start moving to the right. As you move to the right, your x-coordinate gets bigger and bigger, and so does your y-coordinate. Now imagine you move towards the right until your x-coordinate just about gets to 2, but not quite. Now, as your x value gets closer and closer to 2, you can see that your y value is going to get closer and closer to 4. In other words, as you move up this parabola, as x gets closer and closer to 2, y gets closer and closer to 4. Likewise, if we imagine ourselves on the other side of the parabola, or on the other side of the point 2, as x gets closer and closer to 2 from the right side, x squared gets closer and closer to 4. And so we can say that the limit as x approaches 2 of x squared is 4. We say the limit as x approaches 2 of x squared is 4 because as x gets closer and closer to 2, x squared gets closer and closer to 4. Now that might not seem like anything very striking or very important, but this concept has really far-reaching implications. It's a very important fundamental concept of calculus, and we use it a lot. And you'll see as we go through it, it gets a little more difficult. But for now, pretty straightforward. As x gets closer and closer to 2 from either side, y gets closer and closer to 4. Notice, it doesn't matter what happens when we actually get to 2. In fact, it doesn't matter if f never actually gets to 2. The only thing that matters is what happens as we get closer and closer to 2. Okay, limits are all about the journey, not about the destination. It doesn't matter what happens when I'm at 2. It only matters what's happening as I'm getting closer and closer to 2. To illustrate this, let's think of another example. So I ask you to consider this one. The limit as x goes to 0 of sine x over x. Now, of course, you probably don't know what that graph looks like. And so it's a little harder to do it than the last one, but let's go back and think about the last one. In the last one, notice we got the answer by just putting 2 into x squared, right? The limit as x goes to 2 of x squared. If we just substituted this 2 in for x squared, we would have gotten 4. And truthfully, that's a pretty good way to start limits. But you'll see it doesn't work very well in this case. If we substitute the 0 in, you remember from the library of basic functions that you memorized for me the other day, that the sign of 0 is 0. And as x goes to 0, x is 0. And so when we substitute in here, we're going to get 0 over 0, which is undefined. And since 0 over 0 is undefined, we don't know what this limit is. And so we need another approach. Well, one way we might try and do this is numerically. In other words, I told you before that limits are all about the journey and not the destination. In other words, it doesn't matter what happens when x gets to 0. It just matters what happens when x gets closer and closer to 0. So we could imagine substituting numbers closer and closer to 0. In other words, we could imagine coming from the left at -2 and -1 and then getting to 0. Or coming from the right from 2 and then 1 and then 0. Okay, of course at 0 it's not going to exist. We already know that. But if I sub a -2 into this thing, I get decimal 155. You can trust me on that. I ran it through the calculator. When I put a negative 1 in, I ended up with decimal 841. Sorry, don't know why that's there. When I put 0 in, of course, it's undefined. Likewise, when I come from the other side, I see the same numbers. 0.455 when I put in a 2, 0.841 when I put in a 1. And so we could try imagining here, what do you think the answer is as x gets closer and closer to 0? And as x gets closer and closer to 0, you might be tempted to guess that the limit is 1. It seems like it's going towards 1. At the same time, I don't think you'd be absolutely shocked if you found out that it wasn't 1. In other words, if I said, no, it turns out it's decimal 997, that wouldn't be really that surprising, I don't think. Or if I told you, no, it turns out to be 1.0013, you'd think, well, yeah, okay, that's sort of reasonable. We're just guessing what this might go to. If we wanted a better guess, what might we do? Well, we might say, instead of going from -2 to -1 to 0, or from 2 to 1 to 0, maybe we zoom in on it. Maybe we go from 0.2 to 0.1, or -0.2 to -0.1. In other words, we get a better look at this thing. And so what happens if we get a better look at it? Well, if we look at these values, as I come down, at negative 0.2, sine x over x is decimal 993. At negative 0.1, sine x over x is 0.998. Of course, at 0, it's still undefined. It always will be because we're dividing by 0. And when we look from the other side, we notice that this is an even function. So whatever happens on the left side of 0 happens on the right side of 0. And now we look at this. And again, if I ask you to guess, what do you think this function is approaching as x gets closer and closer to 0? You'd probably guess 1. And you'd be a little more confident that it's 1 than you would have been over here. So by looking at it numerically, we can say it seems like the limit as x goes to 0 of sine x over x is 1. We're not really completely certain, but it appears to be going that way. So a numerical approach maybe doesn't give us an exact answer, but it gives us a pretty good idea. We've got a guess. We might look at this thing graphically also. Okay? And if we graph this thing, we end up with a graph that looks something like that. Okay? If you want, we could do it in the calculator just to make sure. So let's give that a try. We'll go in here, and you can do this at home if you want. We want to graph sine x in the numerator over x in the denominator. And when I graph that, I get something which looks like this. And again, I say, well, what does it look like it's going to? Well, it looks like it's going to 1, right? I mean, if I zoom this in a little bit better, I can maybe see it a little closer. And I see that's 0.2, 0.4, 0.6, 0.8. That's 1. And it certainly looks like from the right side it's coming into 1, and from the left side seems to be coming into 1. We think it looks like it's coming to 1. Now, understand, when I get to 0, this function is still undefined because we still get 0 over 0 in that graph. Okay? In the graph, it doesn't look undefined because it's just missing a point. It's missing a hole, and that hole is so small that you can't see it. But we can see that it's there. If I go over to the trace menu and I trace this thing to 0, I see that at 0, it says that the function is undefined, which of course is not surprising because at 0 we have division by 0. So there really is nothing there at 0. But it looks at least very close to going towards 1. And so, again, if we look at the graph, we say, well, it looks very much like the limit as x goes to 0 of sine x over x is 1. Okay? As it turns out, the limit as x goes to 0 of sine x over x actually is 1. But to prove it, we need a more difficult, a more algebraic approach, which I'm not prepared to show you yet. Okay? In the second class today, we're going to look algebraically at solving limits, but even in the second class, you're not going to be ready for this one yet. I won't be able to get this one for you for another, about a month. In a month, I'll be able to show you algebraically why this works. For now, you can just take my word for it. Well, not just take my word for it. You can see numerically up here, it certainly looks like it's going to 1. Graphically, we really feel pretty confident that it's going to 1. And so it turns out that the limit as x goes to 0 of sine x over x is 1. And this is an example of why you can't just trust substituting. Why you can't just take this number and shove it into the function and get the answer. Because in this case, when you put the 0 in, it's undefined. But again, it doesn't matter what happens when x is at 0. It only matters what happens as x approaches 0. Let's take a look at a couple of graphical examples here. and see if we can make a little more sense out of all of this. So here we see a fairly ugly looking piecewise defined function. It's got, a hole in it, another hole, a jump discontinuity here, a displaced point here. We've got some strange things going on. But I think you're going to see that the graphical analysis of this is quite easy. So let's look at the first one. The limit as x approaches -5 of f at x. Well, here's -5. So as x approaches -5 from the left side, the function appears to be going to, did you think 0? As x approaches -5 from the right side, the function appears to be going down to 0. And in fact, that's the correct answer. Okay, as x approaches -5, f at x approaches 0. Let's look at the next one. As x approaches -4. Well, here I notice that when I go to -4, the function doesn't exist there. But as I approach -4 from the left, the function is approaching 5. And as I approach -4 from the right, the function is approaching 5. And since it approaches 5 from the left and 5 from the right, we say that the limit is 5. No problem. Now we look at this one. As x approaches -2, now the little minus sign up here means that we approach -2 from the left side. Only from the left side. So as I approach -2 from the left, I'm coming in from this side. I go up and I see my function is going towards 8. And so I say the limit as x approaches -2 from the left side is 8. What about as x approaches -2 from the right side? Well, now I'm going to -2 from this side. So the limit as x approaches -2 from the right side looks like it's going to 5. It doesn't get to 5. There's a hole there, but that doesn't matter. As it gets closer and closer to -2, as x gets closer and closer to -2, y gets closer and closer to 5. And so the limit is 5. And that brings up the interesting question. What do we do if the question just says, what's the limit as x approaches -2? Well, the problem here is as x approaches -2 from the left side, the function goes to 8. And as x approaches -2 from the right side, the function goes to 5. And so what is the limit as x approaches -2? Well, the limit as x approaches -2 does not exist. In order for a limit to exist, it has to approach the same thing from both sides. So, in this case, because we have a jump discontinuity, because from the left side we're going to 8, and from the right side we're going to 5, we say that the limit as x approaches -2 does not exist. What about f at -2? Well, now this is different. This is not a limit anymore. Limits are all about the journey, but f at x is about the destination. Now I want to know what happens when I actually get to -2. When I go over here and I get to -2, I come up, and I see a hole there, so there's nothing there, so I keep going, and I see that f at -2 is defined up here, at 8. And so f at -2 is 8. Let's look at the limit as x approaches 3 from the left. As x approaches 3 from the left, we're coming in from this side, from the left side, and the function is going down, down, down towards -7. Again, notice it never gets to -7, but it doesn't matter. It's just a limit. We're just concerned with what happens as we approach 3. And as we approach 3, f at x approaches -7, and so that's my answer. What happens when I get there? Well, f at 3, I go across to 3, I look up and down and see if I can find the function, and I find it right there. F at 3 is 1. And so that's my answer to f at 3. And finally, I look at the right-hand limit of f at x. And as x approaches from the right, as x approaches 3 from the right, f at x is approaching 5. And so this is going to be a 5. And what would the limit as x approaches 3 be? Well, again, because when I approach 3 from the left, I'm getting -7, and when I approach 3 from the right, I'm getting +5. If I just say approach 3, it does not exist. Because for it to exist, the left and right limits have to be the same. And so we have a bit of an idea of how to do these limits graphically. And again, just to reiterate what I just said, a limit exists if and only if its one-sided limits exist and are equal. In other words, the limit from the left and the limit from the right have to be the same thing. Let's look at one more example. Imagine this function. Well, this is a piecewise defined function. You've seen these before. To the left of 0, the function is x squared plus 1, which of course is our ordinary parabola shifted up 1 unit. And to the right of 0, my function is 2x minus 1, which is linear with a slope of 2 and a y-intercept of negative 1. So if I graph this, it's going to look like that. The question was, what is the limit as x approaches 0? So as x approaches 0 from the left side, I'm on this function, and that's going to be 1. As x approaches 0 from the right side, I'm on this function. That's going to be negative 1. And so therefore, because the left limit does not equal the right limit, the limit as x approaches 0 does not exist. Okay, you can see it a little bit easier here in the graph. So that's a quick introduction to the concept of a limit. As I said earlier, I know it's not quite the same as you being in class, but I hope that helps. I'm going to give you some homework here to work on. It's page 763 in your textbook, questions 27 to 32. And if you really get badly stuck tomorrow when you're working on this, you can send me a WhatsApp and I'll try and answer your questions as best I can. Okay, I hope you're staying dry, and I'm going to just take a quick break, and then I'm going to come back and try and do the second video. So I hope this helped, and I look forward to seeing you guys on Friday.